read the current structure of the PLC we're connected to if we haven't yet defined our table. We can read the structure and the values. So besides just the fact that this column is a string and this is the first, second, and third row of it, we can read the values that these cells will actually hold in the PLC. And that's a very nice tool to read and check. We can read from a .fdt file. Now very important as well is the read range, write range, and read write tables. With these tools we can say store information in the data table editor here, and we can write it to the PLC. And this is important because if we do this, if we say we wish to create recipes or some information we want to type in and provide to the data table in the PLC, we need to write it, and we'll use the write range. If we've defined information in every cell and column here, we can just select row and press write range, and we'll write this to the PLC's data table. Again, we have the option to verify design. What this is going to do is compare the structure that we've created to the structure in the PLC. Again, this is important if we wish to maintain compatibility between files. We want to make sure they have the same structure. We don't end up with some piece of information that's unexpectedly in a different cell or a different type of information. We can verify cells by range. Again, if we want to select some cells, we can use this. Now I saved the most important tool for last is the memory requirements. I'm going to go ahead and click here. Notice what we get when it finally loads is a pie chart showing us how much space we've used and how much free space we have. Now, I haven't mentioned yet, but we have two different sections of memory to write to the data table. So we break this up as the RAM portion, which is 120K of space that is read and write supported. So if we're using a data logging function, we of course need to use this because we wish to write to the data table. We've defined our table 1 in this space as 2,700 bytes out of our 120,000 bytes. Notice, of course, there's a little pie chart, which is a nice visualization of quickly seeing how much space this table is going to take up. Now I need to stress again that this is the structure of the table which is taking up space. Whether or not we have information in it makes no difference. They can be a bunch of empty cells, but the space in memory has still been set aside for this table. Okay. So we'll look at part of project or flash memory now. And notice, or remember rather, that we did not click any of the part of project options in the column configurations. This is because, again, we wanted to use the read-write functionality of the data table. And if we use the flash memory, we would only be able to read. We wouldn't be able to write. Now you might say, what use is this? If you're creating recipes on the PC and you're going to import them and you have no wish, no desire to ever change them, the part of project is a nice piece of memory to use. We don't have to worry about accidentally having someone write over it or programming an addition that might not work the way we expect it to. I'll give you an example. If we are creating a machine to create paint colors, we have 3 different colors maybe, so we'll have a portion of each color we wish to load, plus maybe some mixing time. This is maybe an idea of a recipe that's not going to change. And the flash memory is a good place to store recipes like this. We can recall them, but we won't change them. Okay. So I'm going to hit OK here. And again, let's just take one quick look. We have, keep clicking that. We have a date, which is again a string. We'll talk about strings in one sec. We have a time, which is a string. We have our data bit, which is our Boolean. Again, high or low, 1 or 0. Our data integer, value between negative 32,000 and positive 32,000 abouts. And our data long, value between negative 2,100,000,000 and 2,100,000,000. So again, we can see the importance in these two different data types there. I'm going to go ahead and close this, and I'll hit yes to save. Okay, so we've defined our data table structure. That is the first important step. Now we are going to create a couple of example functions, and what they're going to do is basically be a data generator. we can't log, or rather it's not interesting to log nothing, so we're going to create a quick example that will give us something to log. So the first piece of information we have is our bit value. I'm going to use a direct contact. I'm going to link it to system bit 13. If you're not familiar with system bit 13, it is high for one single scan every second. And this is nice. Instead of creating a 1-second timer, we can use SB13, and we can have a function that will happen once a second. Again, this is the idea of a single scan transitional element. It's going to be high for one single scan. We don't need to use a positive transitional contact because the system bit is specifically the rising edge. Notice that it's the rising edge of SB3. If I scroll up to system bit 3, we notice it's a 1-second pulse. Now this is a 1-second pulse with a 50% duty cycle. If we were going to use system bit 3, we would have to, in this case, use a positive transition or we'd get some undesired outcome. But very nice is we've included system bit 13 for this purpose. So that being said, we're going to use the toggle coil. The toggle coil, for every scan it's high, will change the state of a bit. And we're going to change memory bit 0, and we're going to call it our data bit. Okay. And we're going to give it a startup value of reset. So when the controller starts, MB0 will start reset. And after 1 second, we will toggle it high. I'm going to hit OK here. And of course you want to give a comment, so we'll just give this example. Bit toggles every 1 second. Okay. We'll fix the spelling later. Notice also, in order to maintain most visual space we have, we can increase and decrease the size of our nets vertically. They are locked horizontally, but one nice thing we can do is just double-click here, and it'll minimize it to its smallest size. And it's nice to be able to see more. So we've created our data bit, and remember we had 3 pieces of data plus the date and the time. So let's create our data integer. In this case, I'm going to use, again, system bit 13. It's a nice tool to use, especially if you're creating simple examples for learning. We're going to use, in this case, the increment function block. And I'll place it here next to our system bit 13. Notice last time I typed in MB0. Another tool we have is the get next unused address. I'm going to go ahead and click here, and notice that we've now selected MI0 as our memory integer we're going to use. Now what this tool does is searches through the list of memory integers and looks for the first one that's not in use. We'll discuss in use in a little bit as well. It's a very important idea to know, especially if we're working with strings, which we're going to in a second. But in this case, I'm going to call it data mi, and I'm going to give it a startup value of 0. Again, this power icon, this plug, means that when we restart the controller, this is the value this memory integer will hold. And maybe in some cases we want to use this, maybe in some cases we don't. If we want to have retentive memory, for example, we don't want it to reset every time the controller restarts. That would mean that we're going to lose whatever value we have in that piece of memory. The memory is, of course, backed up by a battery, and unless we have a function that writes to it at startup, or it's the result of some other function, we expect to maintain the value we have in it. So in this case, I do want to start up as 0. I want to use our incrementer, and I want to count up from 0. So I'm going to hit OK here. Notice the placement of the 2 functions here. I can drag this down like this, but again, for space, I want to minimize the amount of space that one net takes up. So I can do 2 things here. I do have to connect this. I can click here on the Connect Elements tool. Notice I now have a crosshair instead of the mouse. I'm going to hit Escape to get out of this, or I can double click, and again I have my crosshair. And I'm going to draw a line to intersect the 2 ends here. So I'm going to click and hold, draw up, and let go. Okay, hit Escape, I'll get out of this again. And we've connected our elements. Now, we always need to connect the elements from the left to the right. The power needs to flow this way through the net. I cannot connect the output of SB3 to the side here on the increment block. That being said, let's talk about the increment block for 1 second. This is basically a shortcut math function. It's going to add 1 to memory integer 0 and store it back into memory integer 0. And based on the contact we have previous to it, system bit 13, it's going to do this every 1 second. So let's give it a comment. Example int add 1 every second. Okay. Good. So we have our 2 pieces of example information so far. Our third will be the memory long. Oh, you may ask here, what is this piece of data going to do, this memory integer, if we leave it on long enough? Well, we expect it to count all the way up to its upper limit, 32,767, and then on the next increment, it's going to go to value negative 32,768. And it's going to continue increasing from there. The idea is that when we reach the high limit and we increment a little more, we roll over. And if we leave it running long enough, we'll see that, but we probably won't here. Now, we are going to use, again, system bit 13, just because it's really easy, and we're doing a quick example. And this time, we're going to use our math function block. Go ahead to math and select add. And again, I'm going to place it here. And we're going to add, not MI in this case, but we want to use our memory long, so ML. And again, get next unused address, call it data ML. It's going to start at 0 again. And in this case, instead of adding 1 like we did in the incrementer function block, we're going to select const here. And notice that instead of a register value, we can add a constant number. This is nice because these we don't have to worry about storing a value into a memory integer to use the function. This function will always add 337. Okay. And the output, of course, to write back to itself is memory long 0. And of course we have to add the 2 elements, or connect them rather. And we'll give a description. This is the example long add 337 every second. Okay, so our 3 pieces of example data are now going to generate. They're going to generate our data. We can log this to our table now. In the real world, this maybe is the state of a switch or an input, whether the bit is high or low, or input's high or low, or the output's high or low, or a system bit is high or low. An integer or a long could be the current temperature or the current pressure or the value of some register we have running in our program. Whatever information is relevant for our project. So, let's take a look at our data table tools. We click on the menu. We notice we have the drop-down. First, of course, is data tables. This is where we will go if we want to open the data table editor again.